Assalamu alaikum. Today we want to talk about chapter 16 part 2 acids and bases. Section entitled Strong Acids and Bases. Now the chemistry of an aqueous solution often depends critically on the pH of the solution. It is therefore important to determine how the pH of solutions relates to the concentrations of acids and bases. Now the simplest cases are those involving strong acids and strong bases. Now for strong acids, the 7 common strong acids include HCl, HBr, HI, HNO3, HClO3, and HClO4, and one diprotic, H2SO4. These are by definition strong electrolytes and exist totally as ions in aqueous solution. And for the monoprotic strong acids, the molar concentration of H plus equals the molar concentration of the acid. Now, calculating the pH of a strong acid. What is the pH of 0.04 molar solution of HClO4? Since HClO4 is one of the 7 monoprotic strong acids, then it's the concentration of the acid equal the concentration of H plus, as you can see here. So immediately pH equal minus log 0.040 and equal 1.40. Check, because H plus concentration lies between this value and this value, the pH will be between 2 and 1. Our calculated pH falls within the estimated range. Furthermore, because the concentration has 2 significant figures, the pH has 2 decimal places. Now, practice exercise. An aqueous solution of HNO3 has a pH of 2.34. What is the concentration of the acid? Now here, then pH equal minus log the molar concentration of H plus equal 2.34. We multiply by negative both sides, and then we get the molar concentration of H plus equal 10 to the minus 2.34, and this value will equal the concentration of HNO3, which is equal to 0.0046 molar. Now, strong bases. Strong bases are the soluble hydroxides, which are the alkali metals and heavier alkaline earth metals hydroxides. Calcium plus 2, strontium plus 2, and barium plus 2. Again, these substances dissociate completely in aqueous solutions. Now, calculating the pH of a strong base. What is the pH of a 0.028 molar solution of NaOH? Again, because NaOH is a strong base, then the molar concentration of the base equals the molar concentration of OH minus, and it's equal to 0.028. Then we can calculate H plus. You remember from that relationship, H plus times OH minus equals 1 times 10 to the minus 14. We divide this by this to get this molar, and then pH equal minus log this 12.4. Or we can, another method, we can find first the pOH, which is 1.55, and pH equal 14 minus pOH, it is 12.45. Now for B here, COH by 2 is a strong base that dissociates in water to give 2 OH minus ions per formula unit. Thus, the concentration of OH minus aqueous for the solution is in part B is twice the molar concentration of the base, and this equals 0.0022 molar. Then again, H plus can be found by the same way as before, and we determine pH. Or the second method, we find pOH for this value and then subtract it from 14 to get the pH of 11.34. Again, you can solve the practice exercise by yourself, and here you get the answers and check them for yourself. Now, weak acids. For a generalized acid dissociation, HA plus water, A minus plus H3O plus, the equilibrium expression would be Kc, concentration of products, times concentration of reactant. Now the equilibrium constant is called the acid dissociation constant. Now this table shows us the dissociation constant or for some acids, as you can see here. Some weak acids in water at 25 degrees centigrade, and this is a rule. The greater the value of Ka, the stronger is the acid. So if you want to pick the strongest acid, you look at the greatest value of Ka, and it will be the smallest value of pKa. So here HF will be the strongest among all of these. Now calculating Ka from pH. In order to calculate either the Ka value for a weak acid or the pH of a solution, we will use many of the skills for solving equilibrium problems that we developed in previous sections. In many cases, the small magnitude of Ka allows us to use approximation to simplify the problem. In doing this calculation, it's important to realize that proton transfer reactions are generally very rapid. As a result, the measured or calculated pH for a weak acid always represents an equilibrium condition. So let's see this sample exercise. It is here this sample exercise calculating Ka from measured pH. Now a student prepared a 0.10 molar solution of formic acid and measured its pH. The pH at 25 was found to be 2.38. Calculate Ka for formic acid at this temperature. So here, first of all, we put the equilibrium reaction, formic acid, H plus formate ion. Now Ka, concentration of products divided by concentration of reactant. Now pH, from the pH we can determine the value of H plus and then plug it in the equation here. So this is H plus concentration 4.2 times 10 to the minus 3. Then here we construct a table for this equilibrium. Initially 0.10, this is 0. What is the expected change? Minus plus equilibrium concentration 0.1 minus this value and this XX. So, and we make this approximation and we find Ka to be this value. Now the magnitude of our answer is reasonable because Ka for a weak acid is usually between 10 to the minus 3 and 10 to the minus 10. Also here you can solve the practice exercise here, and this is its answer. It is similar to the sample exercise. Now we come to the so-called percent ionization. Now, percent ionization equal concentration of H+ at equilibrium divided by the initial concentration of the acid times 100%. In this example, the equilibrium concentration of H+ equal 3.7 times 10 to the minus 3, and the initial concentration of HNO2 is this value. So percent ionization equilibrium concentration of H+ على the initial concentration of the acid times 100, and it's equal 11%. Now, calculating percent ionization again, a 0.1 molar solution formic acid contains 4.2 times 10 to the minus 3 molar H+. Calculate the percentage of the acid that is ionized. Again, we have this. All these are known, times 100, it's 4.2%. Now again, practice exercise. 0.020 molar solution of niacin has a pH of 3.26. Calculate the percent ionization of this niacin. Of the niacin. Now, from pH here, you see we can determine H+ concentration, and it's equal to this value. So this is the concentration at equilibrium. So percent ionization equal concentration of H+ divided by the initial concentration 0.02 times 100% and it's equal 2.7. Now using Ka to calculate pH. Now calculate the pH of 0.3 molar solution of acetic acid at 25 degrees centigrade. This is the reaction. Ka for acetic acid is given, and now we can look at this table. We construct table again. Initially 0.300, expected change minus x plus x plus x, and the equilibrium concentration is 0.3 minus x, and this is approximately equal 0.3. Since x is much lower or less than 0.3, and then we can find the value of x. Now, as a general rule, if x is more than about 5% of the initial concentration value, it is better to use the quadratic formula. You should always check the validity of any simplifying assumptions after you have finished solving a problem. We are assuming that x will be very small compared to 0.30 and can therefore be ignored. So we ignored that, as you can see here, and we find the value of x, and x will be equal to this value, 2.3 times 10 to the minus 3 molar. So the pH equal this value, minus log molar concentration of H3O plus, and this equal 2.64. Now finally, we can compare the pH value of this weak acid with the pH of a solution of a strong acid of the same concentration. Now, the pH of the 0.30 molar acetic acid is 2.64, as we calculated here. But the pH of a 0.30 molar solution of a strong acid such as HCl equals 0.52. So as expected, the pH of a solution of a weak acid weak acid is higher than that of a solution of a strong base of the same molarity. You see, we use the same molarity. Remember, the higher the pH value, the less acidic the solution. Now let's see this sample exercise 12 using Ka to calculate pH. Now calculate the pH of 0.2 molar solution of HCN, and we can determine the value of Ka or get it from appendix T, and Ka is equal 4.9 times 10 to the minus 10. Again, we put the equilibrium reaction, Ka concentration of products divided by reactant, and this Ka is equal to this value. Now we want to determine H plus. Initially 0.200, change is minus x plus x plus x, and equilibrium equal 0.2 minus x phi x. So Ka equal x times x divided by 0.2 minus x, and this will equal this small value, 4.9 phi 10 to the minus 10. We next make the simplifying approximation. إلى آخره. The amount of acid that is small compared with the initial concentration of the acid. So x now equal this value, 9.9 phi 10 to the minus 6 molar, and this equal H plus. Now, the concentration of this is much smaller than 5% of 0.02, so the initial HCN concentration, our simplifying, is therefore appropriate. We now calculate the pH of the solution, and it's equal 5. Similarly, you can solve the practice exercise. The Ka for niacin is this value. What is the pH of 0.010 molar solution? You can also calculate it. Now, the properties of the acid solution that relate directly to the concentration of H+, such as electrical conductivity and rate of reaction with an active metal, are much less evident for a solution of a weak acid than for a solution of strong acid of the same concentration. So, as a result, the rate of reaction with the metal is much faster for the solution of HCl, the strong acid. So, as the concentration of a weak acid increases, the equilibrium concentration of H+ increases. as expected, but the percent ionization decreases as the concentration increases. Thus, the concentration of H plus is not directly proportional to the concentration of the weak acid. For example, doubling the concentration of a weak acid does not double the concentration of H plus. So the lack of proportionality between the concentration of a weak acid and the concentration of H plus is demonstrated in this sample exercise. Using Ka to calculate percent ionization, calculate the percentage of HF molecule ionized in first a 0.10 molar HF solution and then in another solution. So let's start with the first one. Now Ka from appendix D for HF equal this value. Again, this is the equilibrium. We fill in the table, and then also we make the approximation. We try solving this equation using the approximation, that is by neglecting the concentration of acid that ionizes. We obtain that X equal this value, X, which is the concentration of H plus. Because this value is greater than 5% of 0.1 molar, we should work the problem without the approximation using an equation solving calculator or the quadratic formula. Rearranging our equation and writing it in standard quadratic form, we have this. So X equal minus B plus or minus square root of B square minus 4AC divided by 2M. And then we get this equation can be solved using the standard quadratic formula. Substitute the appropriate numbers and we get X equal this value. So the percent ionization of HF equal concentration ionized على original times 100, and this is equal 7.9%. 7.9%. Of the two solutions, only the one that gives a positive value for X is chemically reasonable. Thus, from our result, we can calculate the percent molecule ionized. Now, for parts B proceeding similarly for the 0.01 molar solution, we have X equal this value, and solving the resulting quadratic expression we obtain, and the percentage of molecule ionized is this, and you see it's 23%. So notice here that if we do not use the quadratic formula, we calculate 8.2% ionization for A and 26% ionization for B. Notice that also that in diluting the solution by a factor of 10, the percentage of molecule ionized increases by a factor of 3. This result in accord with what we saw in a previous figure. It's also what we expect from Le Chatelet principle. There are more particles or reaction components on the right side of the equation than on the left. Dilution causes the reaction to shift the direction of the larger number of particles toward the product side because this counters the effect of the decreasing concentration of particles. Now, polyprotic acids. Many acids have more than one ionizable H atom. These acids are known as polyprotic acids. For example, each of the H atoms in sulfurous acid, H2SO3, can ionize in two steps. So it has two, as you can see, it has two Ka value, Ka1 and Ka2. Now the acid dissociation constant, the numbers on the constants refer to the particular proton of the acid that is ionizing. Thus, the Ka2 always refers to the equilibrium involving removal of the second proton of polyprotic acid. Now, in the preceding example, Ka2 is much smaller than Ka1 because of the electrostatic attractions. We would expect a positively charged proton to be lost more easily from the neutral H2SO3 molecule than from the negatively charged HSO3- ion. This observation is general. It is always easier to remove the first proton from a polyprotic acid than to remove the second proton than the third. Thus, the Ka values become successively smaller as successive protons are removed. Now, the acid dissociation constants for a few common polyprotic acids are listed in this table 16.3, and Appendix D provides a more complete list. Now, the structures for ascorbic and nitric acid are shown in margin. Note that the Ka values for successive losses of protons from these acids usually differ by a factor of at least 10 to the 3. Note that also the value of Ka1 for sulfuric acid is listed simply as large. This value, sulfuric acid, is a strong acid with respect to the removal of the first proton, and the reaction for the first ionogen lies completely to the right. Therefore, it is possible to obtain a satisfactory estimate of the pH of polyprotic acid solutions by treating them as if they were monoprotic acid, considering only Ka1. So let's look at the sample exercise 16.14, calculating the pH of polyprotic acid solution. Now, the solubility of CO2 in pure water at 25 and 0.1 atmosphere pressure is this value, molar. The common practice is to assume that all the dissolved CO2 is in the form of carbonic acid, H2CO3, which is produced by reaction between CO2 and water, as you can see here. What is the pH of 0.0037 molar solution of H2CO3? So we know this is a polyprotic acid. We take the first dissociation here, and we treat it as if it is a monoprotic acid. Why? Because the values of Ka1 and Ka2, they differ by more than a factor of 10 to the 3. So the pH can be determined by considering only Ka1, thereby treating the acid if it were a monoprotic acid. So we proceed as if it is a monoprotic acid, and we calculate the value of X to be equal H plus, and this value equal 4 times 10 to the minus 5. And then we can determine the pH to be this value, 4.4. Now, if we are asked to solve for the molar concentration of CO3 minus 2, we would need to use Ka2. Let's illustrate that calculation using the values of this and H plus calculated before and setting this as equal Y. So in this table now, the concentration of HCO3 minus is this from the previous equilibrium, and H plus is also this. This is 0. With the expected change, we put Y to differentiate it from X minus Y plus Y plus Y, and the equilibrium concentration equal this. Now we use Ka2 now. So this goes with this, and Y equal this value, and this is the molar concentration of CO3 minus 2. And we assume that Y is small compared to this value. Now the value calculated for Y is indeed very small compared to 4 times 10 to the minus 5, showing that our assumption was justified. It also shows that the ionization of HCO3 minus is negligible compared to that of H2CO3 as far as production of H plus is concerned. Now, however, it is the only source of HCO3 minus 2 which has a very low concentration in the solution. Our calculation thus tells us that in a solution of carbon dioxide in water, most of the CO2 is in the form of CO2 or H2CO3. A small fraction ionizes to form H plus and HCO3 minus, and an even smaller fraction ionizes to give CO3 minus 2. Note also that the molar concentration of CO3 minus 2 is numerically equal to Ka2. And remember this point. Thank you. This is end of part